All right, so we are now started onto Unit 3 Energy Flow, Concept 1, focusing on enzymes and biochemical reactions. All right, so let's start out with some Biochemistry 101 and a little bit of review. So, all things are made up of atoms. So, atoms compose all matter on Earth. They have the smallest indivisible particle. Each atom is made up of smaller parts called protons, neutrons, and electrons. Sound familiar? Protons are positively charged and are located in the nucleus. Neutrons are also in the nucleus and are neutrally charged, as indicated by their name. And electrons are negatively charged and are located in the electron cloud outside of the nucleus. And so, atoms are held together through a process called chemical bonding, through bonding. And so this is how we form compounds and molecules. So it's like, think of it like molecular glue holding things together. And so when we're talking about chemical reactions or biochemical reactions, we are actually talking about the breaking and creating of bonds between different substances, which is a process that requires energy. So when we're talking about biochemical reactions, we're just talking about reactions that happen in living things. So that's all that the little tag bio is referring to when we're talking about biochemistry. So once again, chemical reactions are the breaking and creating of bonds between different substances. But what exactly am I talking about? So what is happening really is the atoms in molecules are rearranged to form new ones. So we break apart molecules in the beginning, and we form new ones from those beginning atoms. So we don't create any new atoms anywhere in any kind of chemical reaction. We're just rearranging them. So an example, just so you guys can kind of get a feel for it, is when we combine methane and oxygen to create water and carbon dioxide. So this is an example of a chemical reaction when we have some reactants on the left and some products on the right. And so here is the chemical equation. And I just want you to briefly kind of take a look at the atoms that you see here and just kind of name them to yourself. So can you find all the carbon atoms, the hydrogen atoms, the oxygen atoms, and just do a quick little count and just see what you notice. I'm interested in the patterns that you find. So if you went ahead and did that for a second on your own, which you still have time for, you notice that there's one carbon over here and one carbon over here. Wow. But instead of being bonded to hydrogen, it's bonded to two oxygens. Amazing, right? Those atoms were switched. They literally just kind of jumped ship. And then you look over here and oxygen is just kind of chilling over here by itself. It literally bonded to a second O2 molecule. That's what this number over here on the left means. It means that there's two oxygen molecules. Two atoms of oxygen are bonded together, and then two of those are bonded together. So yeah, chemical reactions, we're just rearranging atoms. We're breaking and forming new bonds. Okay. So all chemical reactions require energy, and so this is something called specifically activation energy. And so it is the amount of energy needed to make a chemical reaction start. And so if we look down here on this little graph, we are looking at a chemical reaction in progress. So it'd be time down here on the bottom. And then on this y-axis, we're looking at energy levels. So if you notice at the beginning of a reaction, we have a certain amount of energy. And then there is a certain input of energy that has to be made before that reaction can occur. And it's kind of like going down a slide. You have to kind of climb your way up that slide in order to make your way back down. So chemical reactions have to climb their way up just like we do when we want to go down slides and have fun. And so a good way to think about this and to remember this phenomenon is by watching this GIF. Okay, so I forget what his name is. I just know it's from the Symptoms. Oh my gosh, Simpsons. I just know that's Bart's son. Okay, and if you notice that he's rolling down the hill, but he does need to put in some initial energy at first. But then once that reaction is started, once he's rolling down the hill, there is no energy needed. He is just flying down there pretty passively. But right at that beginning, it does take some initial energy for him to kind of roll off to the side. And so that's what it's like for chemical reactions. They need a little bit of inputted energy in order to get going. But then once they're pretty self-sustaining. So two very important terms to know when we're talking about chemical reactions are as follows. So reactants or substrates are substances that are changed during a chemical reaction. So remember, there's 5 million different ways to say everything. So reactants and substrates are the same thing. They're referring to the same type of substance. And so if we look down here at this energy diagram again, our reactants would be the initial input of energy, so that initial starting place. And then at the end of the reaction, we end up with products. And these are substances that are made by a chemical reaction. So on this little diagram here, you see that we started out with a specific amount of energy. We inputted some, that was the amount of activation energy, and then that chemical reaction occurred, those bonds formed, those atoms rearranged, and you end up with a new product. So that is something that is made by a reaction. So if we go back to that diagram, an example from earlier, you would see that our reactants or substrates would be on the left, methane and oxygen, and our products would be on the right, water and carbon dioxide. Okay, so before you get that graph kind of stuck into your brain, I want to make sure you understand that there are 2 types of chemical reactions. So overall, reactions either absorb or release energy. And so to describe these concepts, we use the words endothermic and exothermic. So just like exocytosis and endocytosis, we're bringing back those prefixes. So endothermic reactions absorb energy. So remember, endocytosis was when a vesicle fused with the membrane and particles came in. It's the exact same thing. Endothermic reactions are absorbing energy. And so an example of this is photosynthesis, and we'll get into that in just a second. So the diagram over on the left is representing an endothermic reaction. And so it occurs when there is a specific input of energy over here. And by the time that chemical reaction has occurred, you end up with more energy in the products than when you began. Okay. And so exothermic reactions, like exocytosis, are releasing molecules. Exothermic reactions are releasing energy. And so an example of a process, of an exothermic process, is cellular respiration. And we'll talk about that in just a second. And so in exothermic reactions, we start out at this initial energy level, and then we input that activation energy. We reach the amount needed, that chemical reaction occurs, and then you end up with less energy than when you started with. Okay, so our 2 key reactions to never forget are photosynthesis and cellular respiration. So photosynthesis is as follows. This is the equation that you will definitely never forget after we're done with this unit, at least I hope you don't. So the inputs of photosynthesis are 6 molecules of carbon dioxide. And remember, carbon dioxide is present in our breath. So every time you exhale, you are producing carbon dioxide. And so plants use carbon dioxide and combine it with 6 molecules of water, then use the sun's energy and convert those molecules by chemically reacting them and forming new bonds to create molecules like glucose, and then they create 6 molecules of oxygen. So basically, if you try to do the exact same thing on this equation that you did with that last one, you would notice that all of the atoms check out. There's 6 carbons here, 6 carbons here. All we did was we broke bonds between atoms, and we formed them with other atoms to make new types of substances. Well, not new necessarily, just different. And so, photosynthesis is an example of an endothermic reaction because energy is stored as sugar. So, in this glucose molecule, remember that is our favorite molecule to break down, our favorite molecule to use. That is what we use for cellular respiration. So, it is stored energy. So, it is an endothermic reaction. It is absorbing, it is stored, it's inside. Okay, then our second key reaction is cellular respiration. And if you didn't notice already, it is the exact opposite of photosynthesis. And so you start over here on the left with 1 molecule of glucose and then input 6 molecules of oxygen. And after those 2 molecules chemically react, we rearrange those atoms and form new bonds, creating 6 molecules of carbon dioxide. When we exhale, that's what's happening. We just perform cellular respiration and are exhaling out that product. And we also produce 6 molecules of water, and we make ATP. We use energy. So energy is released when sugar is broken down. Therefore, it is an exothermic reaction. Energy is exiting.